Now that we're feeling more comfortable identifying whether a stretch is vertical or horizontal, let's look at some equations that are perhaps problematic for students. We'll start with example A, where we see a blue parabola, f of x, which is defined by 2 times x minus 3 squared minus 8. We know that the 3 and the negative 8 correspond to the vertex, and we know that the 2 makes the graph rise more quickly. That 2 will have an effect on our equation in terms of x, but will not appear in the equation in terms of f of x, as we'll see later. For now, let's determine whether this is horizontal or vertical, and by what factor. So because our invariant points are on the x-axis, we can determine that this has been a vertical stretch. By comparing the vertices, the first at negative 8 and the second at negative 1, we can see that the negative 8 has been multiplied by 1/8 to become negative 1. We know that our mapping rule will show that a value as a coefficient of y. We also know that our equation in terms of f of x will show that 1/8 as the a value in front of f of x. However, when we go to write the equation in terms of x, it will be important that we put the 1/8 in front of a bracketed, in front of the bracketed original expression. This is to say that the 2 times x minus 3 squared minus 8 will all be affected by the 1/8. If we look just inside those rectangular brackets, there are 2 terms. There's the 2 times x minus 3 squared term, and then there's the negative 8. So many students will multiply the 1/8 by the 2 to get 1/4. But it is critically important that you also distribute the 1/8 to the negative 8 to get the negative 1. Let's go back a second. We knew that the blue parabola had a vertex at 3 and negative 8 before we even graphed it. If you were to forget to multiply the 1/8 to the negative 8, then in your g of x equation, it would say 1/4 x minus 3 squared minus 8. But that's not possible because we've already seen that the vertex moved to 3 and negative 1. And so that's why in this new equation we see the 3 and the negative 1. Anytime you're asked to find a y-intercept, you can always replace x with 0. Here, we could replace x with 0 in the transformed version, the g of x form, and we would get 1/4 times 0 minus 3 squared minus 1. And after some work, we would arrive at 5/4. Alternatively, because the original graph, the blue parabola, had its y-intercept at a height of 10, we can simply multiply that by 1/8 to get 10/8, which reduces to 5/4. Now we'll look at part B, where we deal with a radical function. Students are generally quite comfortable with the parabola because we worked on it so much in Math 20. Sometimes we're less comfortable with the radical function, but it's almost easier because you have a clearly defined endpoint, which you know corresponds to the endpoint on the other graph. So here we're given the equation of f of x as being the square root of 32x plus 64 minus 4. I'd like to point out that at this step already, if you factor that 32 out of the binomial under the radical, so that it said square root of 32 bracket x plus 2, that 2, which would correspond to negative 2, and negative 4 would represent the vertex or endpoint of the blue graph. So here, we got to first determine whether this is vertical or horizontal and by what factor. Well, comparing the blue graph to the green graph, we see only one point remains unchanged. The y-intercept at a height of 4 is invariant, as it lies on both graphs. To determine what our stretch factor is, now that we know that it's horizontal, we'll say on the F graph, we had a vertex at -2, or 2 units away from the y-axis. And on the transformed graph, we are now 8 units from the y-axis. Don't talk about moving 6 left. We want to know by what did we multiply. For a 2 to become an 8, we need to multiply by 4. Well, we're feeling pretty good about ourselves having determined the horizontal stretch factor, but be careful, because though it shows up as a 4 in the mapping rule, it does not for the equation in terms of f of x. Remember, a horizontal stretch factor is the reciprocal of the b value. So if your stretch factor is 4, your b value must be 1/4. And that's what we write in g of x equals f of 1/4 x, is the reciprocal of the stretch factor. Now, once we put this into the actual equation in terms of x, remember, we don't have a bracket affecting that 64. We are simply replacing x with 1/4 x. A replacement is always the opposite of the actual effect on the graph. So here, the effect was a stretch by 4, the replacement is by 1/4 x. All that's left to do now is to simplify. Now, the square root of 8x plus 64 minus 4 would be the most simplified version, but a better version would be if we factor out the 8. Why better, you say? Because here we see the h value, or the 8, which shows us that we've been shifted 8 units left off the y-axis and 4 down. But that refers to the original base radical function. So it's a little bit tricky here. I'm not saying that the blue graph shifted 8 to the left. I'm saying if we treated the green graph as being independent from the blue graph, but rather being a transformed version of a base radical function of y equals square root of x, then the 8 out front the bracket would show a stretch by 1/8. The 8 in the bracket shows the translation to the left, and the minus 4 shows the translation 4 units down. That's a lot of information to put together, but I believe that you understand now the difference between a horizontal and a vertical stretch and how to determine the stretch factor. Keeping the stretch factor versus a value and stretch factor versus b value, or 1/b value straight, is another thing, but with time and practice, you'll get it. Having found the equation of the transformed function, it's always a good idea to check this graphically. Here, if we put the f of x function in our calculator and our newly determined g of x function in the calculator, we should see an image that looks the same as we have on our screen. Now notice, we were given a graph that went from -10 to 10 horizontally, but -5 to 16 vertically. You'll probably want to shift your window to these same values so that you really do see the same image. Finally, we're asked to determine the x-intercept of f of x. Now, f of x was the equation we were given, so we don't have to work with our transform function here. Let's go ahead and take that f of x equals square root of 32x plus 64 minus 4 and replace y with 0. We replace y with 0 because an x-intercept always lies on the x-axis where the height is 0. In this first algebraic step, I've actually added 4 to each side, but then just for ease of writing it, I've swapped the sides so that the square root is on the left side. Think back to Math 20. In order to solve a radical equation, we want to square both sides once the root is isolated. So here we square, and on the left that simply cancels out the square root sign over the 32x plus 64. On the right side, the 4 squares to 16. After a little bit of subtraction and some division, we find that x corresponds to 3/2. This means that our x-intercept is -3/2 and 0, or -1.5 and 0. Now, a lot of students will get worried when they get a negative answer for something that had been under the square root sign. But don't worry, because 32 times -3/2 or -1.5 plus 64 gives a positive value. And it doesn't matter that x was negative, it only matters if it generates a negative radicand, which is to say if it makes the part under the root sign turn negative. As an alternate method, because we were given the x-intercept of g of x on the graph as being -6 and 0, and because we know that f of x was stretched by a factor of 4 to generate g of x, going back the other way, we could say, well, f of x is 1/4 of g of x horizontally. So -6 times 1/4 generates -1.5. That said, that strategy is much less often going to be as helpful as recognizing that an x-intercept is when you set y equal to 0.